Okay, so in lesson 23, we are going to look at applications of exponential and logarithmic functions. Primarily, it's applications of exponential functions, but we are going to use logarithms and logarithmic functions to solve the exponentials, just as we saw in lesson 22. So these are all applications. So let's jump right in. Exponential functions can be applied in four ways. All exponential functions are either what are called a growth function or a decay function, and we did address that earlier. So we either have a population that is growing or we have a population that is shrinking. So we use the word shrinking, to represent what we call a decay function. And there are two ways that a population can either grow or decay. They can grow discretely or they can grow continuously. Now, if they are growing continuously, you will always see the word continuously. If you do not see the word continuously, then it is automatically a discrete function. Now, the main difference between a continuous function and a discrete function is that continuous functions have e in them. Discrete functions do not have e in them. They have this term that includes an r. Now, the continuous functions also have an r, but the r is in the power of e. But notice nowhere in here is there an e. So basically we have four kinds of exponential functions. We have discrete growth, we have discrete decay, we have continuous growth, and we have continuous decay. And so these four formulas represent these four different kinds of exponential growth or decay. So the discrete growth formula is this one right here. So write all this down. This is the basic discrete growth formula. P sub 0, or P naught, or initial P, is times 1 plus r to the power of t is equal to P sub t, where P naught is the starting or initial value, like a starting population, okay, or an initial dose of a drug. And then this P sub t, that is the ending value. That's how much it grew to. So it grows from P sub 0 and then it grows to P sub t. And then the r is the decimal rate of growth or decay. Okay, so in this case, it's the decimal rate of growth. So oftentimes it's a percentage, but it's turned into a decimal value. So like if it's 7.4%, it's turned into 0.074. And the way we turn a percentage into a decimal is we take the percentage and divide it by 100. So 7.4 divided by 100 is 0.074, okay? And then t is the time the amount of time that the population grows, okay? And it can be in minutes, it can be in hours, it can be in years, it can be in months, it can be in seconds, okay? And so that is t. T is the time value. In a growth function, the P sub t will always be larger than the P sub 0. So the P sub 0 will always be a smaller number than P sub t because it's growing. So P sub 0 is a smaller number. Then after a certain period of time, it grows to a certain larger number based on a growth rate, okay? It's the same thing in continuous growth. We have a starting value and we have a rate of growth, and then over a certain amount of time, based on E, which is continuous growth, we have an ending value, P sub t. And so again, P sub 0 is less than P sub t. As far as decay goes, though, now the values are shrinking. So in a shrinking exponential function, P sub 0 is larger than P sub t. Okay, P sub z is larger than P sub t. Why? Because the value is shrinking. So P sub 0 becomes smaller and then becomes P sub t. The same thing happens in continuous decay. P sub 0 shrinks and becomes P sub t. And notice we have the R, we have the time in both of them, but notice the big difference between growth and decay. In growth, the R has a plus in front of it. It has a plus. But in decay, the R has a minus in front of it. And that means a negative growth rate or a shrinking rate, okay, or a decay rate. Here with the continuous, the R is positive, but in the decay, the R is negative. Do you see that negative in front of the R? So it's a negative growth rate or a decay rate. So a decay rate always has a negative R, okay? So that's our introduction to exponential relationships, exponential functions. And now we're going to look at a few examples of population growth and maybe some decay. Okay, so here's some examples of population growth and decay, all right? This first one grows, this second one here grows, and this third one is shrinking. So this third one is a decay, okay? So it says a population of 20,000 grows at a rate of 4.7% per year. What will the population be in 7 years? So this 4.7% is going to turn into our rate. This 7, that's our time, t, and this 20,000 is our starting population. So this right here is P sub 0. This becomes our rate. So our rate is going to be 4.7 divided by 100, which is 0.047. And then our time is 7. So t is going to be equal to 7. So we're going to use our population, the word continuously. We do not see the word continuously anywhere, right? So since the word continuously is not present, this must be a discrete growth, formula. Okay, so our discrete growth formula is P sub 0 is equal, it's P0, P naught times 1 plus R to the power of t is equal to P sub t, okay? And we can reverse this. We can actually say P sub t is equal to, we can put it on the other side too. This is the same formula, okay? And but we're going to leave it like this. So P sub 0 is 20,000. So put 20,000 times 1 plus R is 0.047 to the power of t, which is 7, okay? And then I want to add these together. We're going to wind up with 20,000 times 1.047 to the power of 7. And now all we have to do is put this in a calculator. And so we're going to do 20,000 times 1.047 to the power of 7 and press enter. And it says our answer is going to be 27,583.97. Okay, 27,583. And so our population is 27,983. I rounded this to the nearest whole number. Oftentimes we round populations to the nearest whole number because decimal values of a population often are unnecessary. We do not always round them. You'll be told how to round. Now this example says that a population of 20,000 grows continuously. So it's a growing continuously. So we're going to use our P naught times E to the power of R times T is going to be equal to P sub T. Our starting value, again, is 20,000. So we'll do 20,000 times E. E is just a number. Our rate is the same, 4.7. So R is equal to 4.7 divided by 100, which is 0.047. Okay. So to the power of 0.047. Notice we do not do 1 plus here. We just put the 0.047 in the exponent, and then our t again is 7 years. It's all the same information. Sorry, to the power of 7. And now we can just key this in the calculator. So we're going to put in 20,000 e to the power of 0.047 times 7. Now, in some calculators, you'll probably have to put in parentheses around this, and I recommend putting those parentheses in. Execute, and now our answer is 27,792. Oh, I just made a mistake. If I rounded this 96, this 3 should become a 4, so this should be 27,584, not 83. Okay, this should be a 4 here. Okay, and here, this is 27,791.5, so this will be 27,792. Okay, so 27,792. And so you can see that the discrete value is, oh, that's 583. I messed that up. Hang on. This is 27,584. I am so sorry about that. So make that correction. It's 27,584. So the continuous growth gives us a slightly larger number. This is 700, where this one is 500. Okay. All right. Now let's do a decay formula where it's shrinking. So a population of 20,000 shrinks at a rate of 3% per year. So for 3%, our rate, R, is going to be equal to 3 divided by 100, which is going to be 0.03. And again, we're looking at 7 years. So T is equal to 7, okay? Our population, our starting value is 20,000, but it's shrinking. We do not see the word continuous in here, so we're going to use the discrete formula. So it's going to be P naught times 1 minus R to the T power is equal to P sub T. So P sub 0, P naught, our starting value is 20,000 times 1 minus 0.03, because the rate is 0.03, okay, to the power of 7, okay? And let's go ahead and write this now as 20,000 times, what is 1.03 minus, or 1 minus 0.03? Well, let's go back here and let's do 1 minus 0.03, and what we get is 0.97. That is our, that's what's going inside the parentheses here. So this will be 0.97. When this number is less than 1, we know that it's a decay formula, okay? So we'll put 20,000 times 0.97 to the 7th power. And that's what we're going to key into the calculator. So now we're going to put in 20,000 times 0.97, okay, to the power of 7. And we get a 16,159.65. This 0.6 is going to tell us to make this 59 a 60. So it'll be 16,160. So 16,160. And notice now in the shrinking, the answer is actually smaller than the starting number, where in these, the ending number was larger than the starting number, okay? Larger than the starting number. And so those are some examples of exponential growth and exponential decay.